Hello and welcome back to Systems and Network Security. This is the lecture 2, and we'll be actually considering the first lecture as lecture 0. So the modules will be named as 1.1 and 1.2 and so on. So today we have 6 modules, and these modules are all about control hijacking. So the first module, module 1.1, will be on basic hijacking attack, which is done through buffer overflow. Second module 1.2 would be about integer overflow, and this will be a small module. And third module will be on format string vulnerability, which is also a small module. Then module 1.4 will be actually about defenses. So the first 3 modules are about offenses or how attacks are done, and module 1.4 onwards it will be about defenses. So module 1.4 will be about platform based defense, and module 1.5 will be on runtime defenses, and 1.6 will be some advanced hijacking attacks. So we'll be seeing some of the more nuanced attacks, and we'll probably not go into a great detail about those things. So the first module, module 1.1, is about buffer overflow, and as I always do, I must acknowledge the various colleagues around the world whose slides and syllabus I have borrowed from. And so let's get into the details of control hijacking. So what is control hijacking? When a program executes, it has a control trajectory. So usually the program runs from one instruction to the other, and then sometimes there is jump and other instructions that changes the control flow. Now, when the programmer writes a program, he or she has a particular control flow in mind. In our case, when we attack the program as it is running, by control flow hijacking we mean that we change the flow of control towards something that was not intended by the original programmer. And most cases, this change in control is done to execute malicious code or to take over the system and things like that. So let's first look at a very simple example. So here is a C code, and in this C code what's happening is that I have only a main, and in the main I have 2 variables. First one is an integer variable which is called modified, and it's declared as volatile, and the reason why it is declared as volatile is because when you declare some variable as volatile, it is not allocated to a register, it's allocated in the program stack. And then we have a size 64 buffer of characters, and we set the modified to 0 in the beginning, and then we do a getS on the buffer, so which means that a string will be copied onto the buffer. And then we check if the modified is still 0 or not. Now, as you can see in this program, we only assign modified as 0 in the beginning, and then we did not do anything on the modified. So normal logic would say that modified should not have changed, and if it is changed, you would get a message that says that your modified variable has been modified. Otherwise, it prints that try again, right? So now what I'll do is I will use Python, but you don't have to use Python. You can use any other scripting language, or you can write up your own string, large string. So we are basically creating a string of A's. So character A 64 times repeated by this Python code, and then we are passing that to the stack 0, which is the compiled version of this program, and this executable gets in as input 64 A's, and then it puts it into this buffer, and then modified it does not change because we are getting try again, which means that the else part of this code here is executed. However, when we change this to 65 A's, consecutive A's, and then give the same the string where 65 A's have been repeated to stack 0, you will find that you have changed the modified variable. Now, this is something that you did not expect because you did not touch the modified variable, and what we will say is that here is a buffer overflow, and this buffer overflow has modified another variable that is not supposed to have been changed by the program. So let's look at another example, another C code very similar to this one. Same thing, we have a modified variable, we have a buffer of size 64 characters, and then we are taking an argument, a command line argument, and then we are copying this argument into the buffer. So it's very similar, like we were doing getS before. Now we are actually taking a command line argument and copying it using the string copy function. So string copy would copy this argument variable, which is supposed to be a string, into this buffer, and then we are checking whether the variable modified has taken a specific value. So in the previous one, we did not care what value the modified took. It just we wanted to check whether modified has been modified really. In this case, we want to see whether modified has been assigned a very specific value, and then if it doesn't, then we get into the else. So in this case, what we'll do is we'll again use the Python script to create a string of 64 A's followed by 64, 63, 62 and 61 in hex. Now there is a reason for doing this, and we'll explain that later, because here we are looking for 61, 62, 63, 64, and here we have that in the reverse order. And then we basically take this string, its command line argument, and pass it to this executable from this program, and this executable is called stack1, and you will see that you will have changed the variable modified to that specific value. Now third example, again very similar, we have a variable modified, and then we have a buffer with size 64, and then we have a pointer which is called variable, and in this pointer we are actually assigning particular environment variable's value. So this environment variable called greeny, which is not a standard environment variable, will create one, and then this get env function basically will give a pointer to whatever string is associated with the variable greeny, and then we basically check whether the variable is null, which means this in the environment there is no greeny environment variable, in which case this variable will come out as null after the get env function call. But if it does have some value, then variable should have gotten a pointer to the string, that is basically the value of greeny. Then we assign 0 to modified, we do a string copy of this variable, which is a string, and onto the buffer, and then we'll check if modified has gotten this specific value, and if it does, then we say that we have successfully modified the variable modified, otherwise we have not succeeded. So let's see what we'll do to get this working. So first we do an export of environment variable called greeny, and we give it a string of 64 A's followed by this particular sequence of hex numbers, but this sequence of hex numbers will be actually in the reverse order as before, and then we execute the program. In this time the program executable is called stack2, and as you see that since we are taking the string from the environment, we are not going to give a command line argument or some other way of passing the argument, and we'll see that this variable modified is being modified. So why does this happen? And for that we have to understand how buffer overflow works. But before we understand how buffer overflow works, we'll have one more example where we'll be changing a function pointer. So far we were changing the value of an integer variable, but it could be any other kind of variable that we were changing, and in the next example we'll be changing a function pointer. So here we have a very simple function called win, and we want to know if that particular function can be executed by causing buffer overflow. So again, we have a volatile pointer, in this case a function pointer here, and then a buffer variable, and originally the function pointer is assigned null. We get a value from the input into buffer, and if the size of that input is above 64, then hopefully we'll be doing something to execute to change the function pointer variable's value. And if we can change this value to something to the address of this function win, then the function win will be executed. So let's see how we do this. So first we run the nm command, which basically, and then grep this function name win, and then we want to know where the address is, and then this should be in the next line, because that would be our answer to this nm command with the grep. So what this says is the address of the function win is 08048424. So now this time we are using Ruby. I mean, you could use anything like Python as well. So in this case we are actually creating a string of 64 characters, and then whatever is the content of this address, and then we are going to have a we are basically packing this as a binary. So it's not the content of this address, it's a packing the binary, and then you are passing this to stack 3 as argument, and then we'll see that it jumps to the function pointer, because here here the function pointer is being called. Now if there was no buffer overflow, then what would have happened is that initially the function pointer points to null, so this if statement should not have executed. But since through buffer overflow we modified the function pointer value to this particular address, therefore it will jump when if fp is called, then it will be non-null, and then fp will be called, and fp in this case is this particular address, is at this address. So therefore win will be executed and code flow will have changed successfully. So these are 4 examples of how buffer overflow can change the control flow of your program. So these are called control hijacking attacks, and in any of these examples we did not do anything malicious, we just changed some variable values or function pointer value. We'll see that attackers will actually exploit this vulnerability to actually attack your machine or take over your target machine in case of it was a web server, and it can execute arbitrary code by changing the control flow to a location where an arbitrary code or a malicious code is placed. And one thing is buffer overflow, another thing is placing the arbitrary code. So these are 2 different things, and as we'll see that they are often done together. So buffer overflow attack, integer overflow attack, and format string vulnerability, these are some of the examples of control hijacking attacks. But in the last module of 1.6, we'll see that there are other ways, like for example attacking on the heap. For example, we can do this. So a buffer overflow is one of the most common vulnerability, and the first major exploit was shown in 1988 by Morris Worm. So Morris, he actually found that there used to be a program in Unix called finger, and by finger you could actually see who is logged into the system, and whether that person has logged out recently, and what is the email address, and so on. Now this finger was actually a service that was running as what is called a finger daemon, and Morris discovered a buffer overflow in that, and using that he basically exploited that, and that was one of the first examples of internet worm. And then most institutes and companies disable the finger daemon. So nowadays very few places you will be able to finger a user on the Unix system. Now, since then, buffer overflow is one of the biggest challenges, because no matter how good the programmer is and how defensive the programmer is, oftentimes they forget to check the size of the buffer against what is being copied onto the buffer, and then if what is being copied onto the buffer is not is bigger than the size of the buffer, then it will overflow, and when it overflows, it will actually overflow into memory areas where other variables or other function pointers or return addresses are placed, and therefore you will find a change in control flow. So this is a little bit dated, but this kind of holds even today, that about 20% of the vulnerabilities in software are buffer overflow vulnerabilities. So this is one of the very important ones that we must understand and work on. So what do you need to understand or to discover vulnerability of the nature of buffer overflow, or what do you need to exploit and defend against buffer overflow? So first of all, you have to understand how C functions work, the program called stack, the structure of that, and in some cases it's a heap into which buffer overflow is used. So therefore you have to understand how the heap works. Second is you have to know how the system calls are made, and because many times it's the system call that is executed once the buffer overflow succeeds. And then you have to also understand how the exec system call works. Also, the attacker needs to know what CPU and OS is being used on the target machine, and the reason for that is the structure of the stack and how system calls are made, and whether there are already existing defenses and how to circumvent those defenses. Those things depend on what system the exploited program or attack program is running on. And there are slight variations between CPUs and OSs. For example, in x86 you have little endian, and in the Motorola you have big endian. So whether the highest significant bits are placed first or lowest significant bits are placed first depend on the architecture. Also, the structure of the stack frame slightly differs between Unix and Windows. So we'll just take the example of Linux here, and most other operating systems are very similar. So we'll not go into the details of each and every type of operating system and see what kind of stack structure they have. We'll assume that they're very similar, but if you are actually going to exploit them, you have to actually go in and look at the structure of the stack closely. As you know that in a 32-bit operating system, a process has a 32-bit virtual address, which means that it has 2 to the 32 locations that it can address, and this is called its virtual address space. So each process has about 2 to the 32, which is about 4 gigabytes of address space, because addresses basically are for each byte. So so when a program is compiled and run, a process is created, and the corresponding address memory is allocated, and this memory has a particular layout. So here the Linux process memory layout, the entire 2 to the 32 bytes is as follows. So the 1 gigabyte is in case of Linux is the kernel space, and user code cannot read or write onto these addresses, and if it does attempt to do that, you normally get what is called a segmentation fault. So segmentation fault apart, when you are trying to attack a system, if you cause it to have a segmentation fault, that's also an attack, and that's a denial of service attack. But in that case, the program may be restarted again, and it doesn't do, depending on where the program is running. If it is a very critical system, such an attack would be quite damaging. But in case you have an attack that you want to go unnoticed, you would better not crash the system. Instead, you want to do something by the program itself, by changing its control flow to do something malicious. And the interesting thing is that when you do that, if the program is running at a high privilege, for example, as a root user, then you can actually make the program do a lot of damage for you. So therefore, you want to not want to do a segmentation fault. So now, looking at the lower part of this memory layout, the lowest part, lower addresses usually have the code itself, the binary or the image of the process, and this is also usually read only. So this is also somewhere you actually may not be able to write, and if you try, you might also get segmentation fault. Then you have the data segment. Now what data segment means is that it has all the static variables that are initialized by the programmer. For example, if you have static char star gonzo equals something, then that will be actually in the data segment. The next one is called the BSS segment. The BSS segment is where all the uninitialized static variables and globals, they are filled with zeros, and this is where all the non-initialized variables stay, global or static. The next part is the heap segment. This is where dynamically allocated memory is placed. So dynamic allocation happens by taking free spaces from the heap. And then you have something called memory mapping segment. So this segment is actually often not separated from the heap, but what happens is that all the dynamic libraries and on various kinds of mappings stay in this area. And then you have the stack. So this program stack is what we are interested in right now. And interesting part of stack is that while most of the other components of the memory layout increases towards higher addresses, stack starts at a higher address and grows down to lower addresses. So as you will see that when we do arithmetic on stack pointer, you will see how that is taken care of. The growing down is taken care of. So here is the stack, a picture of the stack itself, and I would suggest that you go to this particular website to read about the stack, program stack, more closely. What we have here is a schematic. So what happens is that, first of all, when you have a program and you call another function, a new stack frame is created. So and that function calls another function, then another stack frame is created, and as the program returns, these stack frames are popped off. So you will see a stack basically growing as stack frames. So in each stack frame, what you have initially, the arguments are pushed. So if you're calling a function, the arguments are pushed, and they are pushed from left to right. So if you have arguments A, B, C, then C, B, and A are pushed. Then the return address is pushed. Return address is where the program control should return after the function is over or function returns. Then stack frame pointer points to where this frame starts, which basically means that to the top of the previous stack frame. Then we have the exception handlers, and then you have the local variables, and then you have the saved registers for the callee. So when you will be returning, you will be actually restoring the registers, and then you will be take the return address and put it to the instruction pointer, so that you know where the next after the function returns, what happens next, where it goes next. And then stack frame pointer is used to deallocate the frame. And as I said before, that the stack addresses are going from high to low, so stack grows downwards. So let's look at how this relates to buffer overflow. So suppose a web server has this function, and this function takes a string as input, and it has a local variable buffer of size 128 characters, and then it does a string copy of the string that has been passed to it by onto the buffer, and then it does something with the buffer. It doesn't matter what it does with the buffer. So since string is the argument, so it goes first into the stack frame of the function, then the return address, the caller of this function, where it called, the return address will go back to there, then the stack frame pointer, and then the buffer is allocated. And then this is the stack pointer. Basically it shows the top of the stack. So now suppose this string that I am passing, if you notice that I am not checking anywhere here, I should have checked if the size of the string is below 128 or not. If not, then I should have done something. But since I am not doing that, what will happen is as it copies the string onto the buffer, it basically will, if it is bigger than 128 characters, then it will overflow, and this is what is buffer overflow. And when buffer overflows, then it will write on the space where the stack frame pointer is or where return address is. And that would mean that if I calculate what return address I want, then I can actually create a string that has this exact location where this return address will be rewritten with the malicious code's address. So the main problem here is that the coder or the programmer did not check the length of the string being passed and called string copy, and string copy by itself does not do any of that. So therefore there is a buffer overflow. So now how does one exploit this? So first thing that they can do is they overflow the buffer with a very large string, where it basically overflows across the stack frames, and it places a program here, this program P, that it wants to execute. And then in the return address, it calculates where exactly, it knows the stack structure, so it knows exact return address where this program will be placed. And then what this program is doing is basically doing an exec of the shell. So this is a shell injection attack where a shell will be produced, and then if this program, the original program that has been attacked, runs at the root privilege, then you will get a shell with a root privilege. So this is really bad, but this requires a lot of calculation on the part of the attacker, because it has to exactly calculate where this program P starts, and then put the make the string so that the return address is exactly pointing to this program P's start of the program P, which is basically probably the exec code. So in order to avoid actually exactly accurately calculating the program P's location, what they can do is they can put a lot of nops or no ops instructions, and therefore it can roughly calculate the return address. So if the return address ends up at a nop, then it will keep executing those nops, and then eventually will reach the beginning of program P. So this is what is called a nop slide. So nop slide is the idea that is used in most buffer overflow attacks. So there are, other than nop, there are other things that are considered as nop. For example, if you XOR the same register or do something that is totally unrelated to the original program, you can actually treat them as nops. So creating a nop slide is not that difficult, and therefore you have a little bit of leeway as to how to calculate the return address. Now some complications might be faced by the attacker. For example, if the program P contains the null character, the string termination character, then this will not work, and then the overflow also might actually be overdone, and then it might try to write onto the kernel space, and therefore you might get a segmentation fault and crash the program. So if you want to do a successful attack, you don't want your program to crash. So you should also look at this particular site and see. So CERT is a computer emergency response team, and US CERT is the CERT in the US. There is a cert in India, in Delhi, and many states now, like Maharashtra has its own cert, Telangana is creating its own cert, and they are supposed to collect information about the latest vulnerabilities of well-known programs and then alert different institutes and entities who use those programs and let them know that this kind of an exploit is running amok, and they have to patch their system or do something to avoid being attacked. So the site also has examples of famous remote stack smashing overflows, and so buffer overflow is also called stack smashing. So one example was the Windows animated cursor example, or ANI, and in this case what happened is this, if you go to a particular website, depending on the context, the cursor, when you move the cursor on the browser, it actually shows various pictures, like it could show a little horse or a running horse, an animated one, or an hourglass and things like that. And those files have a very specific structure, and people found in 2007 that by engineering those files a little bit differently, they can actually create a buffer overflow, and this buffer overflow would then be easy to exploit. And it has happened quite a bit, and then Microsoft has since then patched it. But if somebody is running a version from before 2007, then there is a chance that they will actually get exploited. There was also one in semantic virus detection program, and this was actually later on came out because this happened due to some kind of a regular expression library, and we'll actually see even Safari browser later on actually had very similar one. So many functions related to strings that we are used to using in our programs actually are very unsafe for buffer overflow. For example, string copy, as we saw, string concatenation, getS we saw, scanf, and many more. None of them actually does any kind of check on the string that is being passed on to them for copying onto a buffer. And because of that, it's incumbent on the user or the programmer to do that thing, and that is called a input sanitization. So if you do input sanitization properly, then you will avoid this kind of problems, and you can actually still use the string copy and string cat and all these library functions. However, people have suggested that instead of doing using the standard C library functions that don't check account or length of the inputs, you should use this particular functions like string ncopy or string ncat, which basically tells how many characters you are allowed to copy or how many characters you are allowed to concatenate. But they have a problem that they don't check if you leave the string unterminated, because if you just take in characters and that in characters don't have the terminator, then you will not get the terminator. So this could be actually a problem of unterminated strings, and that would lead to again buffer overflow. So Microsoft's string copy _s actually ensures proper termination. So it also checks for termination. So the buffer overflow that we saw until now were actually overflowing the variables, the mostly buffer type of variables, by writing strings onto them, and then we're overwriting either other variables, function pointers, return addresses, frame pointers, and things like that. But there are other things that might be affected by buffer overflow. For example, exception handlers. So if we go back to the structure of the stack that we saw before, exception handlers are also placed in the stack frame. So so especially in C++ and other languages, you have exception handlers for various type of exceptions. So what one can do is they can actually rewrite the address of the exception handler in the stack frame, and thereby when an exception happens, then it will, instead of going to the actual exception routine, it will actually go to a malicious code. So there are two things in this case the attacker has to do. One is cause a buffer overflow to overwrite one of the exception handler addresses. Second is to create the appropriate exception so that that particular handler which is basically pointing to this malicious code to happen. So you have to cause the right exception. Also, in our example, we saw a function pointer was overwritten. So in that case, you are not overwriting a return address from the stack or function pointer from the stack, but you are actually the function itself has function pointers, and these function pointers being overwritten could actually lead to the malicious code. There is also problem with the long jump. So long jump, you should read up on long jump, because long jump is actually a way of creating exception in C, because we know that in C++ we have exception, try and catch, and exception types, but in case of C we don't have that. So long jump is one way of doing that, and also in Perl and so on. So if you can overflow a buffer next to the address, the value that is being passed to the long jump, then you can actually do similar harms. Another thing you can do is you can corrupt method pointers. So method pointers are pointers to methods, and in case of C++, you have virtual functions. So when you derive a class from another class and you want the function with the same function name, you want to invoke a different function when you are an instance of the derived class, then you basically declare a function to be virtual. And in this case, what happens is, in the data structure of the object, there is something called a vtable. Vtable actually contains the address of the various functions or methods that are appropriate for that particular instance of a class. So if you can somehow overwrite the vtable entries, then when that particular function is invoked on that instance of the class, then you will be actually, instead of invoking the right virtual method, you are going to invoke a malicious code. So that's what happens in case of the C++ virtual functions. So how do you find buffer overflow? So one way, of course, there are tools, and we'll talk about them. There are static analysis tools that actually look into the code, analyze the code, and figure out if there is an input that has not been sanitized, which means that has not been checked against the existing buffer size. And this is not easy, because there may be multiple different paths through which this particular value might be propagated. So, but there are tools, and then there are runtime tools and runtime checks that one can do to stop buffer overflow. But in order for quick check on whether your program has buffer overflow, you can do various things. One is obviously to actually create inputs that would induce buffer overflow, and in order to create that input that will cause buffer overflow, you might have to know a little bit about how the program is behaving, what functions it calls, and so on, and what kind of buffer sizes they have. So here is a poor man's buffer overflow finding technique, which is, let's say you have a web server running on a local machine. So you issue a web request with a malform request, and put a marker at the end of this input, and this is actually what is called a fuzz testing. And there are tools that actually create malformed inputs for specific applications. If the web server crashes, then take the code dump and open the code dump and search for this marker. And if there is a marker, then you have found the location of the overflow. So it's actually not something that you would normally do. You would actually want to use tools and other sophisticated techniques, but this kind of sometimes works when you are in a hurry or you don't have many tools at your disposal. So next module will be on integer overflow, which will be a smaller module. So we'll start learning about integer overflow in module 1.2.